Hello everybody. Now that we have looked at moments of inertia, and I hope you all enjoyed the videos with Billy, Bobby, and Bo. I thought they were quite instructive. Just remember that for moments of inertia, we don't have to be able to derive the formula for a particular shape. That's left up to calculus. All we have to do is make sure we understand that the different shapes have different formulas for moment of inertia, and when we are given a regular shape that's in our list, we simply use the moment of inertia formula from that list. Now, we're going to be applying this today to Newton's second law for rotational dynamics. Now, we already know that for objects in non-equilibrium, in linear or translational motion, in the x-plane, we know that the mass will have an x-directed or x-directed linear acceleration if there is a net force in the x-plane. If we're in the y-plane, the mass will have a y-directed acceleration if the net force is not zero. Likewise, with rotational dynamics, instead of force, we talk about torque. And if the net torque is not zero, then the moment of inertia will experience an angular acceleration. Okay? So we're going to be applying this today, Newton's second law for rotational motion. So let's take a look at this first example. In this example, we're given a record on a DJ's turntable. It has a mass of 32 kilograms. And we really do need to go ahead and change that. So 32, not kilograms, grams, would be 0.032 kilograms, and we will need that. It also tells us the radius of the record. The radius is in centimeters, so we do need to convert that to meters. So 16 centimeters would be the same thing as 0.16 meters, and we'll need that. It says when the turntable is turned on, the record starts from rest. So we know the initial angular velocity is 0. It accelerates to an angular velocity of 3.5 radians per second. So that will be the final angular velocity. And it does this in a time of 1.2 seconds. If we consider the record to be a uniform solid disk, determine the net torque producing rotation. Okay, so we want to find the net torque, and we know it's a solid disk, which is a regular geometric shape. So we go to page 243 in our text, and we find out that the moment of inertia for a solid disk, SD for solid disk, the moment of inertia is 1/2 the mass times the radius squared. Okay? All right. Now, we are trying to find the net torque. We know that net torque, need an N, net torque equals I alpha. Okay? We also need the acceleration because we're not given the acceleration. But look what we do know. We have some kinematics information. Now, we have plenty to understand and remember that the angular acceleration is the rate of change in angular velocity. So, final minus initial angular velocity divided by the time period gives us the acceleration. So now what I can do is I can simply take these two formulas and substitute them right here, and we can easily calculate the net torque. So the net torque is going to be moment of inertia, which is 1/2 mr squared, times the angular acceleration, which is omega sub f, minus omega sub O over T. Okay, now we can simplify that a little if you wish. First, the initial angular speed is 0, and that's going to leave us with mr squared omega sub f divided by 2t. So I just simplified it a little bit. If we plug in our information, the mass is 0.032 kilograms times the radius squared, so that'd be 0.16 meters, and don't forget to square it, that is a common boo-boo, and the final angular speed of 3.5 radians per second. We're going to divide all of that by 2 times the time, 1.2 seconds. All right, if we stick this into our calculator, then we will get a value of, if I remember right, 0.0012 Newton meters, which is the unit for torque. All right, so see, moments of inertia are not all that scary, guys. Don't let it fool you. We already have standard formulas for regular shapes. So all we have to do is use them. Okay? Now, look at this example. In one of the videos that you watched yesterday, you did see a demonstration with a solid wheel like this with a mass on each side. Now, which way will it rotate? Well, it stands to reason from our linear dynamics that we've learned about, our translational dynamics, that obviously the mass that is the heaviest is going to accelerate down while the smaller mass will accelerate up. So that means that this wheel is going to rotate clockwise, okay? That just makes sense from our point of view. We know that has to be true. So let's see what we have here. We have a uniform solid wheel or solid disk. So knowing that, then we know that the moment of inertia is going to be that of a solid disk, just like it was above. So we're going to use 1/2 the mass of the disk times r squared. Okay? The radius of the disk is given. All right? And if we show it right here perpendicular to the line of action of one of these string forces, we can see that the radius of the wheel is also the lever arm for the weight. In fact, I can go ahead and draw the two weights that are acting tangentially upon the wheel. So we have mass 1 and mass 2, and I'm going to call this T1, and this one would be T2. Okay? Now, before, when we looked at pulleys in dynamics, we said T1 and T2 had to be the same. But they're actually not here, because you have a flywheel or a uniform disc that is not massless or frictionless. Well, in this case, yes, it is a frictionless axle, so it does turn frictionless, but it's not massless. This disc has appreciable mass compared to these two. So the two tensions actually aren't going to be the same here, and each one is producing a torque, but it will rotate in the direction of the net torque. Since this is the bigger force, the net torque will be in this direction. Now, so if we want to look and find the net torque, let's see, we've also got the mass of the wheel itself, big M, and big M is 3 kilograms. We also have the radius of the wheel, which is, 0.25 meters. But in this case, the radius is also the lever arm for each of these two tensions, okay, from the axis of rotation out to the line of action of the force such that it's perpendicular. That's the lever arm. So this is also the lever arm for the two tensions. Okay, so determine the net force. Not force, torque. The net torque, in this case, we cannot find using using I times the angular acceleration, because we don't know the angular acceleration yet. So we have to go back to the other definition of torque. The net torque is the sum of the torques acting on the flywheel, and there are two. So we're going to have T1, and in this case, T1 is the weight of mass 1. So that's going to be M1G times the lever arm, which is R. Okay? Now, what kind of rotation would that produce if it were the only thing acting on the wheel? Well, it would produce a counterclockwise rotation. So I'm going to put a positive there. Now let's look at the second one. The second mass is pulling down this way. So if we look at the direction it rotates, it has a rotation that would be clockwise, and that's negative. So I'm going to put negative. M2G is the force, and its lever arm is R, the same R. Okay, so there's our two torques, force times lever arm, force times lever arm. We've got to combine those to get the net torque. So we get 0.8 kilograms for mass 1 times 9.8 times 0.25, which is the lever arm, minus 1.6 for the other mass. Oh, is it one? Yeah, 1.6 times 9.8 times the same lever arm value. Okay, now if you stick that into your calculator, you should find that the net torque has a value of negative 1.96 newtons. And because the sign on the torque is negative, then yes, it will rotate clockwise. All right? So the negative means it will rotate clockwise. All right. Part B wants us to determine the angular acceleration. Well, we just found the net torque, and we know the moment of inertia right here. So we can say the angular acceleration from Newton's second law for rotational dynamics would be the net torque divided by the moment of inertia. So instead of A equals F over M, we get alpha equals net torque divided by moment of inertia. All right, so that'd be negative 1.96 newtons. Newton meters. Let's put the Newton meters on there. Newton meters divided by 1/2 the mass of the wheel, which we are told is 3 kilograms. Yeah, don't use the other two masses. This is the mass of the wheel, the rotating object. And then times r squared, so 0.25 meters squared. Don't forget that square. And if you stick that into your calculator carefully, you should end up with an angular acceleration of negative 21 radians per second. Now, the negative. All right? If we look at the angular speed using our right hand, the axis of rotation comes out of the page towards us, okay? But it's rotating counterclockwise. So we have to rotate, clockwise, not counterclockwise. We have to rotate our hand. Now we're looking down on top, and our fingers rotate clockwise, but our thumb is now into the page. So the angular velocity points down into the page. And since it's speeding up, the angular acceleration points the same way as the angular velocity into the page. Okay? Into the page of the paper, into the plane of the paper, because you are accelerating, not decelerating. Okay, that's it for this lesson. You do have an assignment why don't you try working on that? And I think I stuck in a couple of little sample problem videos that you can look at also that are helpful.